And welcome back to our double operatic theory of systems lectures. We're going to follow off today where we ended last time. Just to recall, maybe I'll go up a few slides. What we were looking at is composing more machines. And so more machines, we had were these kinds of abstract machines with a set of states, a set of inputs or parameters, a set of observations or outputs, and these two functions, one which sort of gives the view, which exposes some variables of state or gives us some observations of state, and the other one, which is the update, which takes our parameter, our input, and gives us a new state. And then we saw that this general form is very similar to whether you want it to be a deterministic update or a stochastic update or a possibilistic update or even an ODE. And we'll come back to all those variations later, but for now we're just going to focus in on how these kinds of Moore machines, these deterministic Moore machines, compose. So we were composing these Moore machines by sort of wiring them together in this way, and we were extracting the formulas from the composite by looking at the wiring and thinking hard. And that's what we were doing last time. So we had composites like this where we could compose them together, multiple wires in, multiple wires out. We could use feedback, and we were actually just writing down the formulas for the composites directly. So here, for example, we took these formulas and we extracted them out of this wiring diagram, but it wasn't exactly clear how we were doing that. So what we're going to do now is show how using this notion of lens, we can give a very precise definition of the wiring diagram and a very precise exposition of how the wiring diagram act on systems. So a lens is this thing over here. And it is a pair, the category of lenses has, its objects are pairs of sets, and the morphisms are the things that are called lenses. That's very much like when you're in the situation where you have the category of relations, where the objects are sets and the morphisms are relations, but we still call it the category of relations, or the double category of spans, which we'll come to shortly, where the objects are sets and the morphisms, the loose morphisms in that case, are spans. So lens is like one of those, and we'll see that that's for good reason, in fact. So a lens here is a pair of functions of this signature, which is a little weird. As you can see, it goes forward from A plus to B plus, and then it goes backwards from B minus to A minus. But when you're going backwards, you're also allowed to use an extra input from A plus. Now, spans form a category, and the way they compose is in this corner down here. And I've written it, so the bottom composes just straightforward. And then the top, you compose using this formula up here, which you see copies A plus and passes it forward using F, so that we can use it in the pass back by G and then use the pass back by F. And so I wrote that out in this form here because this is a pure categorical form. And you can see that this only depends on the universal property of the product. And so, in fact, we'll be able to do lenses in any Cartesian category. So this will give us deterministic, discrete time Moore machines, but where our updates and our readouts are allowed to be are expected to carry extra preservation properties like continuity or measurability and so on. So the thing we observed at the very end of last time is that a system, a Moore machine, is itself a lens of this form. If you just set both the things in the back to be the same, then the two maps of the lens become a map, the exposed map and the update map. And so by lens composition, you'll note that if I take such a thing and I compose by any other lens, the resulting composite still is of the form that the back two are of SS. So this must give us a new system. And so lenses act on systems on the right by composition. So we're now gonna see how that works. So let me just select. Let's look at this in more detail. And we remember that we started with a system. This composite here, if we look at that formula above, is going to be, this composite is going to be a new system. And so let's write out what it is. Well, the new E is defined to be the composite of these two things, the old E, and then whatever W was, to O prime. That's the formula above. And the new update, new U, is U prime, let's say, and it goes from S, and then it takes in an I prime, and it gives me a new S. And the formula for that is up above on the screen. It is U prime of S I prime equals, now we use the F sharp up here would be the update U here. So it's an update of S. And then what is the second component? It's the W sharp here, as I've written it, of the F of A plus. What is that? Well, here the F is the E. So that's E of S. And then we take the I prime over here. So that's our new update. So what I want to show is how this kind of composition of systems is a general formula that takes one system and produces a new system, right? A new Moore machine. How this encodes the wiring diagram composition we saw before. But before doing that, let me describe how we have a that lens here is a symmetric monoidal category. And we define the tensor product of objects, also known as the parallel product, to be just the Cartesian product on both constituent sets. Now, of course, for this to work, we also have to give a tensor product for lenses themselves. This is known as the parallel product. I'll write it up. And we'll see why in shortly. And on the bottom, it's simple. But on the top, we actually have to do a little thinking. It's roughly speaking going to be just this. But that wouldn't have the right type signature. Because let's actually think about what that type signature has to be. It has to go from A plus times B plus times A times, I guess I didn't say what the other two are, but let's just say it's C minus times D minus into A minus times B minus. That's what that one would be. And you can see that what we have is A plus times C minus to A minus. This is F sharp, and we have B plus times D minus to B minus, and this is G sharp. So you can see we almost can apply it, but what we have to do is say that first, this is isomorphic to, we have to just rearrange the factors, A plus times C minus times B plus times D minus. And then we can do F sharp times G sharp. All right. So what does this do to systems? Well, the reason I call it the parallel product is if I have U1, E1, U2, E2, this will be from S1 times S2 So note, the top and bottom of the left-hand side are still the same, so it still is going to be a Moore machine into I1, I1 times, oh, gosh. I1 times I2 over O1 times O2, right? That's just the type signature of this. And what it's going to be is, well, E1 parallel product E2, right, is going to take S1, S2, and it's going to give us E1, S1, E2, S2. That's nice and easy. And the update of S1, S2 at I1, I2, well, it's just going to be a pair of states. And what it is just going to be the update of the first and the update of the second. And so as you can see, the reason this is called the parallel product is because we take the two systems and we join them together, we couple them, but they don't interact at all. So this, I claim, is going to correspond to this wiring diagram. S1, S2, I1, I2, O1, O2. And as you can see, we've composed the systems in parallel. So again, parallel product. Now remember that a box with multiple wires in is interpreted as being the same thing as taking in a single wire that represents the product of the sets that those wires carry, whose elements those wires carry. And so you can see that this does indeed give us has the correct signature, that because we have I1 and I2 coming out, we have I1 and I2 up here, similarly O1 and O2 here, O1 and O2 here, and you can see that the product of all the state spaces is exactly the state space of the composite. So now we will render any composite of systems in two stages. First, we take this parallel product, and then we take a unary product on a unary coupling, wiring diagram, I should say, on the resulting thing. So let me show you how this works. If I want to do this diagram here. So now I'll just call these A, B, C, S1, S2. So this one, I will say, it's really nice to write it as a sequential product, but we can see that, in fact, this can be rendered into a two-stage construction. S1, S2. And then we have an intermediate stage here, where first we do the parallel product. So this is A, B, B, C. And then we take the B here and we wrap it around all the way down like that. So the outer, so as you can see, this is the inner coupling is the parallel product. And the outer one is this, what I would call unary coupling. In other words, it just takes an in box. We have these two wires each. It's A, B, B, C. We pass the A's, the A gets passed straight in, the B gets passed straight out, and the B gets looped around like this. Or if I drew that a little nicer, so I could redraw this, right? This is the same thing. It is one we have seen before, where if I put the B's up top, because it sort of doesn't matter what order I pass these in, then it's the same thing as this one. You see, I've just reordered it. Okay, so what you can see is that first, in this two-stage process, to do this composite, that is it. We can do first the parallel product. So we take, so we have here S1, S1, U1, E1, A, B. And then we do the parallel product of this with S2, S2, B, C. And this is going to give us a system of this form. S1, S1, parallel product, S2, S2, U1, E1, parallel product, U2, E2, A, B, parallel product, B, C. And that is what happens in this inner box up here. So this new system is this intermediate stage system. Then we're going to take this wiring diagram and we're going to post-compose it like this. We're going to put it here. So let's do that. This I will call WW sharp for that wiring diagram. And what is its signature? Well, as you can see, the inner part of the wiring diagram is a box with two B's and an A and a C. It is precisely as you can see here. We have this A, B input. Here's the A, B input. And I'm sorry, it has the AB input, which is these ABs, excuse me. And it has the BC output, which is these BC. And we're going to send it to something which has only an A and a C. And has an A input and a C. So what could this be? Well, I'll draw it under here because it's going to correspond to this diagram. So as you can see, just to draw it again, it's A times B, B times C to A, C. And what is it going to be? Well, it's two maps. Excuse me. Again, it's a lens, so I've just written out the signature. And then we can say what it is. Well, W, B, comma, C, what is W? W is the output that is induced by this wiring diagram. So when I have when I take in a BC, in other words, I look over in here and I imagine that my wires carry something, and I'm asking, what do I see on the output wire here? Well, it's obvious. I take my B and C, I forget about the B because I don't care, and I just read directly the C. So that gives me my formula, WBC equals C. Similarly, when I look at the update, the backwards pass here, it takes in three things. It takes in a BC and an A, and it has to give me something. So what is it doing? Well, when I'm looking at here, the AB here is the inner input. This AB is the inner input. And what I'm asking is, given the outer input, this A, which is here, and the inner output, which are this BC, how do I set the inner input? And again, we can see that the wiring diagram tells us. We take the outer output, which is an A, and we pass it directly into the inner input. So the outer input, which is an A, we pass it into the inner input, which is an A. So there's our A. And then the B we get from the inner output. So it's the B. So very simple formula here. Just to Okay, but now let's compute what this composite is on the left. So first, right, we compute this part just to be sure, right? So remember here, we had E1 parallel E2 of S1, S2 is equal to E1, S1, E2, S2, and U1 parallel U2 of S1, S2 uh, takes in S1, S2, and it takes in an input from both of these. So that's an A and a B. And that's going to update them both independently. So it's a U1, and the U1 takes in an input A, so it's S1A. And the U2 takes in the input B, so it's U2B. U2S2B. 2B. So that's what that one is. And then we can compose it with the W's that we computed before using the formula for composition, which I'll bring back down so we remember. Put it up near the top. Okay. I think we can see what's going on now. So now, right, our formula for composition, we're going to take the new combined composite one is going to be W after E1 parallel E2 on the bottom. So what is that? Let's compute it. So it takes S1 and S2, and it equals W of E1 of S1, E2 of S2, but W of BC was C, so that just equals E2 of S2. And what do you know? If we go back up, what would the output of this wire be? Well, on C, we're only going to see the output of S2. So that is correct. Going back down. Now the fun bit, right? We ask, what is the composite of the other one? So the new sort of U prime here, the combined U prime. Well, what does that do? It takes in an S1 and S2, and then it takes in, well, all the way out, takes in this A, and it's going to give us this formula from below, but now the F sharp is U1 bar U2, and the G sharp is W sharp. So I'll write that out. U1 parallel U2 of the A plus here down here is the S's. So S1, S2, and then we take in a pair, which is the result of the W sharp of now it's E1 parallel E2 S2 comma A. So I've just written out the formula from below in the current language. And then we can compute this because we know what the U1 and U2 do. U1 of U2, and then we have to say this pair, right? The pair, by the way, is going to be the two elements here is the first projection of W star. Right, it's a pair like this. And then in here, these two holes are going to be filled by whatever this is. So let's compute that by looking over here. we see that it takes in two things and it gives us this pair. So the first one of these, we're going to put in here. And that is the A. The second one of these, we're going to put in here. And that one was this B, which is the first component of this one, which is E1S1. And what do you know? That formula there says that if we want to update this combined system on an input A, we first update the first one on A, and then we update the second one on whatever the output observation of A was. And that's exactly what we said before last time should be the interpretation of this sequence of wiring. So it's a long road and it takes a lot of computation, but the main point is we've now completely systematized this. So I'm going to get even more systematic by giving you yet another presentation of what these lenses look like that will make it quite clear that wiring diagrams are lenses in three Cartesian categories. So lenses as spans. Okay. So I suppose I should start by saying what spans are. Spans and pullback. I think I want to assume you know what pullback is. I'm struggling to exactly pitch this lecture series, but definitely a second course in category theory kind of thing. Maybe that's not right. I'll just say what it is. The pullback, here's my reminder. The pullback in sets is going to be a completion to a square. Like this. And we mark this square by this little corner to say that that square is a pullback. So that for any other set, T, and any two functions like this, if I call this f and g, this pullback is the pullback of f and g. So any two x, y, there exists a unique x comma y like this, so that this diagram commutes. So P we can take to be the set of all pairs x, y, and x times y, such that f of x is equal to g of y. So if I take a span now is something like this. And if I take two spans and I line them back to front like this, I can now take the pullback here, which sometimes we write as times sub b t. And that gives me a composite of spans. Now, this is almost a category. I don't quite want to get into, well, I don't know. I don't quite want to get into how it isn't exactly a category right now, but it has to do with if you iterate this process, you end up with the problem of x, y, z versus x, y, z. Oh no. Those aren't equal sets. If I take the set of all these things and the set of all these things, they're not equal sets, but there's an obvious bijection between them given by reassociating. And you get that problem with span. So you don't get an associativity for span composition by pullback, but you do get an associativity up to this very nice isomorphism. Okay. Now, so it's worth noting that these are isomorphic, but another nice thing to note is that they're all isomorphic to the triple list. And that turns out to be a very nice way to express how nice these isomorphisms are. It's just noting that, in fact, we could remove all the inner parentheses and have them there. No matter how deeply nested these parentheses get, you could always just remove them. And doing that is a bijection. So Okay. This gives us this kind of thing. If these are all in set, this gives us a construction span set. And we'll come back to what makes span set special. It's actually not just a category, or as I've sort of been wobbling here about exactly what it is. It's actually a double category, and that sort of gives us a nice way of understanding exactly what it should be. But now what I want to show you is how we can get lenses as spans, not in set, but as spans in some other kind of construction. So consider the category, right, which I will write as set semi-direct product set, defined in this way. Objects are product projections. A plus times A minus projecting onto A plus. The notation is chosen judiciously. And morphisms or maps are squares. A plus times A minus to A plus. B plus times B minus to B plus. F and F bar. Now this is quite straightforwardly a category, because if we, these are commuting squares, I have to say, right? It's quite straightforwardly a category because we can just put these squares next to each other and gives us associativity. But I want to actually note that this category presented here, that F bar, because it's going into a product, we can actually express it as a pair of functions. You know, F bar is equal to a pair of two functions, the second one of which I will call F sharp. The first one is going from A plus to B, A plus times A minus to B plus. But remember that we actually know that this square commutes. And the first one is the first, well, maybe, sorry, I should have written it like this, and we'll do it like this. The first projection of F bar and the second projection of F bar. There we go. So the first projection we actually know, because by the commutivity of the square, it is F after the first projection of onto A. The second one I'm going to define to be F sharp. And we note that this one here goes from A plus times A minus to B minus. So in fact, this is a very similar, very, very similar to a lens, except that in a lens, we would have had B minus, A plus times B minus to A minus. So it's sort of a dual to a lens, very similar. Okay. So set times set has a functor to set given by the first projection. In other words, it projects out the codomain, is what I should say. Oh, maybe I should write down what the composition is in here in terms of F sharp. So in other words, what I'm saying is that F bar of A minus, A plus, A minus is equal to F of A plus, comma, F sharp, A plus, A minus, by definition. And then if we have a composite, right, it would be a composite would be like this. Right? As you can see, the bottom here, the bottom composite is going to be G after F. The top composite is just going to be G bar after F bar. But we can actually the question we can ask is, what is G bar after F bar sharp in terms of G sharp and F sharp? And we can just sort of read it out. It's the second component, right? So as you can see, because this is the second, it's going to take an A plus and an A minus. It's the second component of the resulting map. So what we do is it's clearly G sharp of F bar of A plus A minus. And we know what that is. So it's G sharp, or sorry, I shouldn't be calling it sharp. I should be calling it flat. Excuse me. I'm going to reserve sharp for the lensy ones and flat for this direction. Excuse me. Of F of A plus, comma, and then here, F flat of A plus, A minus. Yes, thank you. So that's just like what the second component is. By definition, defining G flat to be the G over bar flat to just be the second projection. And so you can see that that looks also similar to the lens composition. If we go back and see what the lens composition was, similar. Okay. So now what I want to say is that, okay, so we have this functor to set, and what it does is it takes A plus times A minus, projecting onto A plus, and it gives us A plus, and it takes a square and it gives us just F. So this functor is what's known as a fibration, sometimes a Grothendieck fibration, or also a Cartesian fibration, which is, I think, what I'll call it. And the reason it is because we always have pullbacks of this form. If I have A plus to B plus F, and then I have a map like this, B plus times B minus, I can always form the pullback here. And the pullback I can form is going to be of this sort. I'm going to take A minus to just be B minus. And so at the top, as you can see, I'll just take F times id. And at the bottom, I have F. And maybe I should note, we could also, as you can see, the data of an object here is roughly speaking A plus and A minus. And as we saw here, the data of a map is the data A plus, A minus to B plus B minus. But now we can write the arrows going in the same direction because they both go in the same direction. They go from A minus to B minus. So we write this like that. Just to give you something that looks like lens notation. So this thing here would be A plus B minus 2, and then I'll put the equals in here because that's the F sharp here was the identity. B plus B minus. So any morphism in here that is a pullback like this is called Cartesian.
You said sorry, flat is the identity, but I guess it's like projection.
Yeah, yeah. It is, so this yeah, it's correct. F flat is not the identity, it's actually projection onto the component, but I will still write the thing like this. It's fiber-wise the identity. Thank you, Mateo. It's fiber-wise the identity. Over A plus, it becomes the identity, if you will, of this. Okay. So then there's another kind of map we can have is the opposite. Sort of. We could take A plus times A minus to A plus. And then we can imagine that we have an identity over here, A plus, and then just something else over this. And now we could imagine that we have some map up here. Well, F bar, this would correspond here is F and then id. It's not exactly correct, but this is morally what you want to think. Or maybe I should be exactly correct and say it's pi 2. And here we would have A plus, B minus, A minus, and here we have an equality in the bottom and a map up here, and this is just id F sharp. And these have a nice, there's a lot of nice properties of these, but the first thing to note is that every square can be factored into these two, because if I have any square, where'd it go? If I have any square, A plus times A minus to B plus. And this is F and this is F bar, then I can write it in two stages. So first, I can put the F sharp. So in here, I'll do id, comma, F sharp. And then here I'll do F. And then here, I'll take the pullback map here. So F times id. And you can see that the top does compose to F bar, again, by definition. By definition, F bar was equal to the pairing F comma F sharp. Or I guess it's not by definition. The second component is by definition. The first component is by us, checking. And so this is a factorization like this. But even more usefully, if we have, so that's a, but more, so this is a Cartesian. This one's called vertical, I should say. And the reason it's called vertical is because it lands into, it's an analogy from differential geometry and connections in differential geometry, so which I'm not going to go into, I guess. But this is like a change in the top that doesn't change the bottom. So if you write changes in the bottom horizontally, a change in the top that doesn't change the bottom must be vertical on the page, which is really where this word comes from. But we can just take it as a word. So now we have a lemma that every vertical Cartesian square has a pullback in set semi-direct product set. So let's write what that is, but I'm going to use this other notation because it will be a little easier. So I'm going to start with the bottom. And then what do I mean by vertical Cartesian? Well, I mean that this one here is going to be Cartesian, which remember meant that it only had a bottom thing. And this one here is going to be vertical, which means that it only has a top thing. Is that the way I want? Sorry. There we go. They go in. There we go. That's right. So these are both, in other words, the shape here is something like A, C, B in here, and we need a P that forms the pullback. But now we're doing it in set. So all of these things are pairs. So this is A plus, A minus, B plus, B minus. And now we need to give something up here. Okay. Well, first, we actually know a lot more about A plus and A minus because we know that the left leg is Cartesian and the right leg is vertical. So I'm going to give a name. This is F, and this is pi 2 because it's Cartesian, and this one's vertical. So I'll call this G sharp. Again, it's flat. Excuse me. G flat. This is it. So we have these two maps, right? So we know, first of all, that the bottom is id. So in fact, there's no B plus. It's in fact also a C plus. And on the other hand, we know that this top one is just the identity here. So this is no A minus. It's in fact just a C minus. So in fact, our situation really looks like this. So what can we put up top? Well, remember that we need a pullback. So a priori, we would have two maps like this. But it's not just that. It has a pullback in set, and the pullback of Cartesian is Cartesian, and vertical is vertical. If we take that extra, which sounds like it's more difficult to prove, but if we just decide we're going to do it, then this one would also have to be vertical. And this one would also have to be Cartesian. And when we decided to do it like that, you see that there's only one thing we could possibly put up top. Because for this side being vertical says that the bottom of the top must be A plus. And this side being Cartesian says that the top of that of the back must be B minus. So now we just have to find maps from A plus to C plus and maps from well, I guess this is pi 2. Maps from A plus to C plus and maps from as you can see over here, it's going to go from B minus A times A plus times B minus to C minus. Well, we actually already have those. F is already one of those. Over here, it's already a map from A plus to C plus. And G flat is already a map from C plus to B minus. So we need to put something up there. The thing up here has to go from A plus times B minus to C minus. And what the G flat is, it goes from B minus, sorry, it goes from C plus, oops, C plus times B minus to C minus. And so it's not clear what, we don't have exactly the right thing, but remember, we do have a map from A plus to C plus already, namely F. So we do F times B minus. And then down here, we now can do G flat. So up here, we actually put G flat after F times B minus. Okay. Now it remains to check that that's a pullback. I'm gonna leave that as an exercise. It's not terribly difficult. Remember that if you have any two maps into the other two sides, they have to commute at the bottom. Since you have a lot of identities around, that sort of, or projections and identities, that sort of tells you a lot about what those two maps in could possibly be already. Okay. So now what that means is we can actually take spans in this set times set, or not set times set, semi-direct product set, but where we're only going to use the left leg will always be vertical and the right leg will always be Cartesian. So what do I mean by that? Well, that here, right, would mean it was a span. So I'll take A plus A minus, X plus X minus, B plus B minus. It's a span in set direct product set, which looks like this. But the left leg is supposed to be vertical and the right leg is Cartesian. So actually it's a span like this. Now let's see what this does. Right? Oh, so my point is that you can always compose these. And why can you compose these? Well, if you had two of them, then we know you can get the pullback here. Now, to write down that pullback, we should actually use the facts we know about these being, so this, because the left line is vertical, this has to be A plus here. A minus. This has to be A plus. And because the top one there is because this one's Cartesian, this has to be B minus. Just has to be. Similarly, on the other side, we don't actually have choices. B plus C minus. And up here, of course, by looking at this formula, although the names are all different, right? We have to take this one here. This one here has to be of the form A plus, and this one here has to be of the form C minus. And that is the one that we would have to get on the outer one. And so let's look at what this actually this actually does here. Oh, and I should note that it's sort of straightforward to see that the composite of Cartesians is Cartesian and the composites of verticals is vertical. So that the outer ones here, the true composites here, are also of the correct form. So now, what is the data here? Well, there's two bits of data. There's this one on this side, which is id something, which I'll call G flat. Well, actually, let me not just rename things all the time. This one I'll call F sharp. And this one I'll call F, pi 2. So each one of these spans has two functions of data. But you can see that using just the signatures we already calculated by the fact that they had to be vertical and Cartesian, we must have F from A plus to B plus, and we must have F sharp from A plus times B minus to A minus. So it's a lens. And now we can actually check that, in fact, this gives us lens composition. So if this is G sharp over id, and this is id over G flat, or it's not really id again, but whatever. Then here, I'm going to have to compute what that is.
Should that be G flat or?
This is just should be G. It's G. Right. So now I can use the formula up above to compute what these ones are. So this one's easier. So I'll do that first. This one just has to be F. Id. And therefore the left-hand side is just a composite on the bottom. So it's G after F. Id. And that's good because that's what the bottom of the composite of lenses was supposed to do. And now the top, right? What is the top here? Well, the top here, we have to do G flat, or sorry, just to make it, we have to do, it's in this case, it's G sharp, as I've written it down here, G sharp, after F times C minus. So I renamed the things. That's the one up top. And then we have to compose that after by F sharp. Right? So that is, in other words, we're taking F sharp of, and then, well, we have to put in, if you remember the formula here for the composition of these things. You see, the composite takes the second one here, the second one flat, applied to the first one, applied to the first thing, and then the first one, second component applied to both. So if we go back down here, we write that up. This might take a couple watches. And please follow along with your pen and paper, or this will not make any sense. You really have to do it yourself for this to make sense. F sharp here will take in, well, it's the bottom one of the first component, which here is the identity on A plus. So it just takes in an A plus. And then it's the other thing here, which is G sharp after F times the C minus. So it's G sharp after F of A plus C minus. And what do you know? That was our weird formulation from before about lenses. So in other words, we have that span set semi-direct, oh boy, set semi-direct product set vert cart is equal to lens in set. Right. So now I can actually tell you how we could get lenses of that would include the tangent bundles and do ODEs. So I'm now going on to recovering the lens story for more machines into ODEs so that we can couple ODEs this way. Okay, so here's the thing to know. So what we used here is that we had these two classes. We had vert and cart were classes of maps in set, right? Stable under pullback along each other, which is a way of saying that we had pullbacks of verticals along Cartesians and the resulting tops were vertical and Cartesian respectively, the resulting tops of the square root.
I guess you could choose it such that there exists a pullback with those properties.
Yeah. Yeah, so here we have, in other words, just to say, it's like vert, sorry, just to do it in the way I really want it. We have cart, we have vert, and then we get a pullback where this is also vert and this is also cart. And that way, if we had vertical Cartesian spans, you see that we get a composite of vertical Cartesian spans. So we only need some category with this notion of vertical and Cartesian. And that notion of vertical and Cartesian was defined relative, if we go back up, to the projection from set times set to set. Because vertical meant that that functor up here, which projected a square onto its bottom, its codomain, Vertical meant that when you project, you get the identity. And Cartesian means that the square is Cartesian, which is a certain universal property that says if you have something like this, which is a partially filled square, you can universally lift it to a totally filled square. In general, this is always going to work if you have some notion of bundle, like these arrows, that can be pulled back using pullbacks. So in particular, we can do another situation here where my claim is that I'll call this so I'm going to call this linear dependent lenses. And I'll note for any type theoretical people watching, I mean linear into like actually like linear algebra, not in the sense of linear type theory, because there's another thing you could call linear dependent lenses that would be linear in the sense of type theory and dependent in the sense of type theory, but I'm not meaning that. On manifolds. So here we have the notion of vector bundles. So vector bundles is a category. Its objects are vector bundles over manifolds. So I'll encourage you to look that up if you want to see the real definition, but the main idea is that for any point in the manifold, we get a vector space as a vector space over R, and it sort of smoothly varies in the point. This VP is known as the fiber over P. Right? And a map is just a commuting square. So maybe I'll call this Vn, and this is Vn. A map is a commuting square. And so it's a theorem that vector bundles pull back. So you can always, if you have this situation, move it. Can I move it? Oh, whoa, it's teeny. All right, whatever. If you have this vector bundle V over N, you can pull it back to get something called F upper star V over M. And it's defined by the relation that F upper star V over P is defined equal to be V over F of P. Which is a sort of general, if you will, sort of adjointness property between notations here. Okay. So in particular, an example of a vector bundle example is the tangent bundle. The fibers are the tangent spaces. So remember, if your space was actually embedded in Rn, right? This is M, and your point P is here, then the tangent space is actually the plane, terribly drawn. The tangent space is actually the plane that is tangent to that point. And when you consider that point itself to be zero in that plane, you can then add vectors coming off of it, and you get a vector space. Those are called tangent vectors. So that's the way to think about this. There's sort of abstract notions that are coordinate free that don't require an embedding, but in most cases of modeling practice, you often have an embedding, and you can actually use this themselves. Okay. Moreover, I mentioned that if I have any function like this, and we've already sort of seen this when we looked at representability of trajectories, any function f, we actually get a whole square like this. And this is a map in vector bundle. I should say this. This has to be fiber-wise linear. In other words, Vm at P to Vn n at Fp This is F over bar, this is F. F over bar at P is linear. Now, that's not strictly speaking necessary to ask. In fact, you could do this at a greater generality, but I think it's nice to think about it this way. So it is true that TF, right? TF at P is what we saw before is the derivative of F at the directional derivative of F at P. I don't actually know the notation for this. I totally forget, but it's the directional derivative. It takes a vector at P and it gives you the directional derivative of F at that vector. So, okay. So now we note that we have this pullback. So we can say that we have this pullback up here. So we can take span vector bundle vert cart, and that we will take to be our definition of lenses. Lenses of vector bundles, say. Okay, and so what does that mean? Well, let me give you what a lens into the tangent bundle would be, because that I claim is going to be a system. So we'll take TM, we'll take M, and then we'll take something that I'll just call IO, and this is a vector bundle. So now I need a span, so it's X to Y, some other thing. But remember, the left leg has to be vertical, so this has to be the identity. So it's in fact not Y, it's in fact already M, or I shouldn't call it M, I'm going to call it S, excuse me. Because we always do. And on the other one, I want this to be a pullback. So I have some map here, which I'll call E, and I need the top to be a pullback, which means that that's not an X, it's an E star of I. The pullback. And then I need a map this way, and I'm going to call that U. So my claim is that this is a parameterized system. It's a parameterized vector space. And and let's see how that works, right? So one thing I'll say, first of all, is suppose we did this, but we started with the terminal, so R0, the terminal vector bundle, which is just a single point and the 0-dimensional vector space fibered over that point, right? Then I write down this diagram. This here is E. We have E star of the point. And then we go here, and this is U. But now it's a general fact that if you pull back an identity, you might as well take it to be the identity. This one's a pullback. The data of E is trivial here because it's a map into the point. There's only one of them. And so the only actual data in such a diagram is this map U, which you can see it has to make that square on the left commute. So in other words, this is a section of the tangent bundle, i.e. a vector field, i.e. we have ds dt, we have this equation, the equation equal u of s, as we saw earlier on in the series. So in this case, right, we can understand what is the pullback here. It's actually given by the pullback in sets, correctly topologized into a manifold, which is not obvious, but it does work when you have a vector bundles, and in general, it will work if the projection is a submersion, surjective on tangent spaces. So what is this? Well, it's pairs of S and I, but there's an equation, and that equation is that E of S is equal to pi, if I call this pi, of I. Okay, let's look into that a little bit later, but right now what we can see is that U of SI is now a function, it's a tangent vector, or maybe so, right? So we get the equation dsdt equals USI. And now we see that we've arranged to have this extra parameter I. Now, the condition over here says that in fact the parameter space is allowed to vary with the output, right? But the parameter you actually take has to be valid for the current state you're in. Right? An example of where that might make sense is if your space is a sphere, increasingly squat, and then your output, say, was also just the whole sphere, and your input was some force that is going to be tangent to, so if this is P, this is O, this is I sub P, this tangent space up here, that is tangent to it. When we pull back this, again, we're pulling back an identity, so it's going to be the same thing. But then here, it's a tangent bundle again. These are all the tangent bundles, in fact. But now, that's not an equals. Tangent bundle. But now here could be an actual function, U. And you see it's a function that's going to take in a state U of S and I is a tangent vector you already have. So you can imagine, for example, that you experience some kind of force on you that is tangent to your existing position. And with that information and your current state, you give an update, because maybe you don't just copy through the force, maybe you actually also have some countervailing things coming from the state itself. And this would be the dynamic. This is a case where your dynamical system needs to do that. But most often, of course, you could just take this instead to be O times I to O. And then that would be a constant parameter space I. Okay. Now, the fact that this U has to be linear on the fibers does mean that you have to satisfy this equation. But that's actually inessential to the whole thing. You don't have to add linearity on the fibers. The whole story would work if you didn't ask for linearity on the fibers. But the way I'm doing it is that. So you also get lenses in here, and lens composition is given still by pullback, and it works just as the other story. So when we come back next time, I'll talk about how, so we've seen that you have more machines can be given by lenses in set. We've seen that ODEs, parameterized ODEs, can be given by lenses and vector bundles, where we had to use this other definition of lens to make it work right, which is originally due to David Spivak. Next time, we'll see how we can take wiring diagrams and compute the lenses that relate to them in an entirely formal and very nicely categorical way.